Greetings to respected Madam Sirs. I am Pavan Sai from the Department of Computer Science and Engineering, Artificial Intelligence and Machine Learning, Section C. Today I'll be presenting on the topic titled Understanding Crystallographic Access in Applied Physics. This presentation mainly focuses on the concepts of crystallographic, specifically the importance of crystallographic access in understanding the internal arrangements of atoms within the solids, which has direct applications in engineering and material section of science. So, undertaking the crystallographic access in engineering physics. Crystallography is an essential area in applied physics which deals with internal structures of solid materials. This presentation aims to introduce the fundamentals of crystallography and empathize the importance of crystallographic access. Understanding the arrangement of atoms in solids, if not only in theoretical subjects but also in practical necessity in the fields such as electronics, materials engineering, nanotechnology, and material mechanical designing. The spatial orientation of the atom impacts material strength, conductivity, and the thermal properties, and these can be analyzed through the study of crystallographic and access. Crystallography basics. This section introduced the basic concepts related to crystallography, starting within its definition, significance, and clarifications of crystal types. And the definition of crystallography. Crystallography is defined as the scientific study of the arrangement of atoms in crystalline solids. It involves in determining how atoms are geometrically positioned in regular repeating patterns called as crystal lattice. By understanding the shapes and the structure of the crystal, scientists and engineers can explain the predict the materials, physical and chemical behaviors. Crystallography is an essential in identifying unknown materials, analyzing defects in solids, and improving the performance of the device that relies on the solid state property. Importance in physics and engineering. Crystallography plays a key role in the several branches of science and engineering. In material science, it helps in developing materials which specific electrical and mechanical or thermal properties. In solid states, physics crystallography explains the phenomena such as electrical conductivity, magnetism, and superconductivity. In applied physics, this knowledge supports the design of durable structures, high performance electronics, and the precious optical components. It also helps in predicting phase transitions which occurs when the material changes its own state to another, like from the solid to liquid or from one crystal to form another, affecting the fundament functionally. And the types of crystals. Crystals are classified based on the types of atoms and bordering forces and the whole board together. There are four main types: ionic crystals, covalent crystals, metallic crystals, and molecular crystals. Coming to the ionic crystals, these consist of positively and negatively charged ions which are held by electronic forces. They have high melting points and dissolve well in water. Example, sodium chloride. Covalent crystals. Atoms are linked by covalent bonds, forming hard substances with high thermal resistance. Explaining example includes diamond and silicon. Metallic crystal. Compounds of metals atoms share free electrons, forming a sea of electrons that allows to conduct electric and reshape easily. Example, copper, iron. Molecular crystals built from individual molecules held together by weak van der Waals forces or hydrogen bonds. These have low melting points and include substances like ice and sugar. Each type has its unique mechanical, electrical, and optical properties, making them suitable for specific applications in engineering and technologies. Crystallographic access. Now we shift our focus on the main concept, crystallographic axes. This section explains how they are what their orientations and why they are matter in real life world applications. Now we define the definition and the significance. Crystallographic axes are imaginary reference like which are used to describe the geometry and symmetry of a crystal. In the crystal lattice, we define three main axes A, B, and C. They describe the unit cell, which is a small repeating unit of crystal. These axes from a 3D coordination system that helps us to describe the position of the atoms or molecules inside the structure. They also allow for standardization, comparing and categorizing crystal across the different materials. Understanding these axes, which is important for interpreting crystal systems, analyzing diffracting patterns, and predicting the directional behavior materials under stress or temperature changes. Axis orientation and description. The orientation of crystallography axis is sympathized of as follows. A-axis generally aligns with lengthwise directions of crystal unit cell, often the longest axis. B-axis lies perpendicular to the A-axis, repeating another dimensions. C-axis, the third axis that may or may not be perpendicular to the A and B depending on the crystal structure. These axes helps in describing the crystal's symmetry. For example, cubic crystals have three axes of equal length and an angle 90 degrees, while monoclinic or triclinic systems have unequal axes and non-right angles. Crystals may be classified as primitive with atoms only at concerns of the unit cell or centered with additional atoms inside the cell which impacts the crystal structure and the physical properties. Application of material science. Crystallography axes are widely used in material science and applied physics for practical purposes. Characterize the crystal structures. These axes has determined the integrated arrangements of atoms, allowing the researchers to understand how structures influence material properties. Nanotechnology and semiconductor designs. The orientation of crystallographic axes uh, affects the behavior of semiconductors in crucial fabricating microchips and nanoscale devices, which are tiny in size, very tiny, which can be looked by a magnifying glass. With to look at it, we need magnifying glass, which helps us to focus on the chips or the alignment. Phases, transitions, changes in axis orientations of symmetries are often associated with chain charges in the material states such as melting, solidifications, or transformations. In a new phrase, by understanding crystallographic axis, scientists can develop more effective, durable, and advanced materials for using in electrons, aerospace, and constructions, and more. Conclusion. In the conclusion, crystallography and specifically the concept of crystallographic axis, which is a fundamental aspect of applied physics, by studying how atoms are arranged and oriented in solids. Researched and engineers can predict the controlled material properties. This knowledge plays a critical role in developing of new technologies, advancing materials and engineering solutions. Whether it's designing better semiconductors or creating heat resistant alloys, understanding crystallographic axis provides the foundation of processing in multiple science and industries domains. Thank you. Also, I want to conclude my presentation. Thank you all for your attention. Thank you.